In this course, we are going to talk about a lot of different functions. And as you'll see, it's going to be important for us to have a good language for describing functions, a language that is clear and concise and consistent. And that's the purpose of this lesson, to come up with a good way of describing functions. Now, it's a pretty long lesson, so I'm going to split it up into two separate videos, and you'll want to be sure to check out the second part of the lesson as well. So let's get going. Before we get into some ways of describing functions, I just want you to notice that you've already been doing this quite a bit. Here are several of the base functions or parent functions that you've used in the past. We have our familiar linear function, which is a straight line, our quadratic function, which is a parabola. We have our square root function, our reciprocal function. We've worked with several exponential functions using different bases. We have our trigonometric functions here and our absolute value function here. And we've done several things with these in the past. We've drawn their graphs, we've transformed them, and so on. Now, we are going to look at several properties of these functions that we can use to describe them. These functions here, as well as other functions coming up in the future, functions that are more complicated as well. And we'll start with this function here, the one shown in the graph. Now, I don't have an equation for this function. We're just going to use the graph. And just note that this function does not continue to the left past the next value of 2, or to the right past the next value of 9. So one of the things that we've used to describe functions in the past is domain and range. And that's where we'll start here. What is the domain and what is the range for this function? Well, as you know, the domain is just the set of all of the x values that the function uses. And in this one here, we have lowest x value of 2. And we use all of the x values right up through an x value of 9. So our domain, we have x is an element of the real numbers such that x is between 2 and 9, and includes 2 and 9 as well. Similarly, we can describe the y values, the set of all y values that this graph uses. That's what we call the range. Our lowest y value is 1, and we actually use all of the y values up through a y value of 6. So our range, we have y is an element of the real numbers such that y is between 1 and 6, including both 1 and 6. So quick review there of domain and range. Another thing that we can use to describe functions is a description of where the function increases and decreases. And it's a pretty simple idea. Informally, if a function is increasing, that means that it's rising from left to right. And if it's decreasing, that means that it's falling from left to right. The important thing here is that when we look for where a graph increases and where it decreases, that we're reading that graph from left to right. So let's take this function that we just saw and talk about where it increases and where it decreases. So first of all, where is it increasing? Well, from left to right, we see that from here to here, it is increasing. Now, remember that when we talk about where something happens for a function or on a graph, we always refer to the x values. So we would say that this function is increasing from 2 to 4. Okay, from left to right, from 2 to 4, those x values, this graph is going up. Okay, and we have another interval of increase as well. We see that right here, from an x value of 5 through an x value of 7 here, we see that the graph is also rising, so it is increasing, okay? And we can express those intervals using our regular old inequality notation. So from 2 to 4, for an x value of from 2 to 4, the graph is increasing, and for an x value from 5 to 7, the graph is increasing. Where is the graph decreasing? It's decreasing on this interval right here. So how would we describe that? That's the interval from 4 to 5, again referring to the x values. And also from 7 to 9, we see that the graph is falling or decreasing there. So our intervals of decrease are 4 to 5 and 7 to 9. Now, I will draw your attention to something very important here. At this point right here, this little peak, and this one here, we do not consider that to be an interval, part of an interval of increase or decrease, because at those points, the graph is neither increasing nor decreasing, is it? It was increasing before that point, and decreasing after it. But at that point, it isn't doing either of those things. So we do not include these values. For example, here we do not include the 4 because it's not increasing at that 4. A similar thing happens, when we're talking about a point where we go from decreasing and change to increasing. We would not include this x value of 5 when we're talking about this interval of decrease. Notice that all of these less than signs do not include the equality with them. Okay, so there's a nice way we can write these intervals, a little bit more efficient. If you don't want to write the interval 7 to 9 using inequality notation like this, you can actually write it like this. Now, we're used to seeing points on the plane described like this, like an x value of 7 and a y value of 9. But if we're talking about an interval, we can also use this notation. And in that case, what this means is the interval 7 to 9, just like this. And it's talking about x values in this case, from an x value of 7 to an x value of 9. This graph was decreasing. The fact that we're using round brackets here, that indicates that we're not including 7 and 9. In a case where we wanted to include a 7 and a 9 using this notation, we would use the square brackets instead of the round brackets. Okay, so you have the option of using that notation if you want to. And it just says here that we do not include the endpoints when stating intervals of increase, decrease. Now, we already talked about how we don't include the points at the little peaks there where it changes from increasing to decreasing or vice versa. We also do not include the endpoints here when we're talking about intervals of increase and decrease. We really need to see points around what we're talking about when we're talking about increasing and decreasing. So we don't include the actual endpoints in those intervals. Okay, now we do have some formal definitions. Here's a formal definition of what it means for a function to be increasing. And now it looks a little bit complicated, perhaps a little bit scary, but let's just read the first part of it here. It says a function f is increasing on an interval I if f at x1 is less than f at x2 whenever x1 is less than x2, and x1 and x2 are in I. And there's a similar type definition for decreasing there. But let's take a look in a little bit more detail about what that formal definition means. Now, the first thing you might be asking is, why would we want such a formal definition? And the reason is because there's no room for misinterpretation with this definition. With our informal definition, there's a bunch of things, a bunch of details that have been left out. But with this definition, it kind of covers all of the possible questions that could come up. So let's take a look at this part here where it talks about what it means for a function to be increasing. And we'll do a little graph, and on this graph, I will just make a segment of a function that actually is increasing, and we'll see why this definition makes sense. So it says a function f, that's our function here, f, is increasing on an interval I. Okay, so we need an interval I. So perhaps this is just a piece of a function, and let's say it's from an x value of 4 up to an x value of, it really doesn't matter. Let's just say 15 here. And that interval, we're calling that I. So that's where the function is increasing, okay? So what does it mean for it to be increasing? Well, it says it's increasing if f at x1 is less than f at x2 whenever x1 is less than x2. So we need a couple of x values, specifically 2 of them, where the first one, x1, is lower or less than the second one. So I can do that. I'll just maybe draw a little line there. That's our x1 value, and our x2 value will be right here. So I should be able to do this with any x1 and x2 point that lie in my interval I. So that is in the interval from 4 to 15. But I'm just choosing a couple specific ones for this example. Let's see what happens for the corresponding y values here. Do we get the y value for x1 ends up being less than the y value for x2? Well, we will, because if we go up from x1 to our graph, the y value for that point would be whatever f at x1 is. Okay, this is a graph of y equals f at x. Similarly, if we go up from x2 to our graph, the y value for that point would be f at x2. Now notice what happened. Our f at x1 value ended up being lower than our f at x2 value. That is, our y value for x1 is lower than our y value for x2. That has to happen if you have an increasing piece of your function. And you can probably imagine I can choose any x1 and x2 here. As long as I choose x1 to be the lower of those two values, so it'll be on the left of x2, we're always going to get this happening. The y value for x1 will be lower than the y value for x2. Think about that. That always has to happen if the function is increasing. So that's what the definition is saying. If no matter which x1 and x2 you pick in this interval, if you always get that f at x1 is lower than f at x2, that means you have an increasing function on that interval. And the same thing happens with decreasing. The only difference is here, your f at x1 value would end up being higher than your f at x2 value. And I'll leave it to you to just draw a little graph to convince yourself that that would be the case if that function is going down from left to right. So that's the formal definition. And it's a very thorough definition, a little bit wordy, but it kind of, like I said, it covers all the details that we need. Okay, so let's head back to our properties and let's talk about a new one. Okay, so what's next here? Yes, absolute extreme values. Another pretty simple idea here. Informally, we have an absolute maximum at the highest point on the function. So the absolute maximum of a function is its highest point. All right, so there's our familiar graph again. And you can see here this function f has an absolute maximum at the point 0.76. That is the highest point that this graph passes through, that this graph uses. And when we talk about where is that absolute maximum? Remember, we refer to the x value. So that absolute maximum occurs at 7. That's the x value. Now, what is the absolute maximum value? Well, that's the y value. That's the highest it goes, which is 6. Okay, so what the value is, the absolute maximum value, is talking about the y value. And as a courtesy, when we state the absolute maximum value, it's acceptable to just say it's 6 because that's the highest it goes. But we often state that using our function notation too and say, yeah, that's f at 7. Which is 6. And that way, anybody who's reading this knows that the highest the graph goes, the absolute maximum value is 6. But you can also see that that occurs at an x value of 7. Same idea for absolute minimum. This is just the lowest point, and our function has an absolute minimum right there at 2. Again, the x value is what we use to describe where it happens. And the absolute minimum value is, well, that's the y value for that point, which is 1. And again, we usually state that that is actually f at 2, which equals 1, just so we know where it's happening. Okay, so that's just, again, reiterating that when we talk about where something occurs, we're talking about an x value. When we talk about what the function's value is, we're referring to the y value. Again, we have a formal definition. This one's a little easier to understand than the last one. It's just saying that a function has an absolute maximum at a if the function's y value at a is greater than or equal to the function's value for every x in the domain of f. It's just saying when you sub in a, you get a y value that is higher than all of the other y values, or at least, not lower than all of the other y values for your function. In that case, f at a, the y value for a, is the absolute maximum value. And the same thing for minimum here. You've got an absolute minimum at b if your y value for b is less than or equal to the y value for all other x in the domain of your function. All right. Okay, moving on. Local extreme values. What's this all about? Well, informally, and there's our graph again. Okay. If we restrict our attention to just a specific region of this graph, take a look at this region right here. Ask yourself, if we're just looking at that region, do we have a maximum? Just think about that for a sec. Look at it. We do. At that point, 4, 5, right here, we have a maximum. Now remember, that is not the absolute maximum for this function. That occurred right here. But if we're just focusing our attention in this region, that's a maximum. And we think of it like in this neighborhood, in this area here, in this region, if that's a maximum, we call it a local maximum. Okay, just in that neighborhood, in that locality, in this vicinity, this is a maximum. So that's considered to be a local maximum. What is the local maximum value? Well, again, that's the y value, which is 5. And it happens at an x value of 4. So we would say that f has a local maximum value of 5, which is f at 4. Okay. Now, does that mean whenever we have a little peak like this, where the graph goes from increasing to decreasing, that we have a local maximum? And the answer is yes, that is very much true. Now, a local minimum is the same type of thing. If you have, if you're just focusing your attention on, say, this area of the graph, this point here would be a minimum in that region. So locally, in that area, that's a minimum. That's why we call it a local minimum. And the local minimum value here is 3, and it happens at 5. Okay, so we have a local minimum value of f at 5, which is 3. And this point that just came up here is just saying that we actually have another local maximum value as well. It's right here, and that one was also the absolute maximum value. Remember that? But because we have in this region, we have that peak, that maximum, that's also considered to be a local maximum. And the value is f at 7, which is 6. Now, one question that often comes up is, what about the endpoints? Now think about that for a second. What about the endpoints? We didn't discuss those. That is, this point here, 2, 1, and this point here, 9, 2. Could we, or should we, consider those to be local minimum points in this case? I don't know. What do you think? Should they be? Well, depending on whose book you read, you might get a different answer. In the book for this course that we use, endpoints are not considered to be local maxima or local minima. Okay, in this course, the only way we get a local maximum or a local minimum is if we see the change from increasing to decreasing or decreasing to increasing. You need to see this little hump in the graph here, like a camel's hump, or this little valley, for it to be considered a local maximum or a local minimum. Okay. Now, other books, for example, the one that's used in our AP Calculus course, that book does consider endpoints such as this and this to be local minimum. But in this course, we are not going to do that. And I mentioned this before. Remember, we started by looking at the interval from 2 to 5, and I wrote it like this. I included the 2 and the 5 when I referred to that. If you want to do that using our new interval notation with brackets, just make sure you use square brackets to indicate that we're including the 2 and the 5. Now, by the way, if I didn't include the 2 and the 5 here, I'd still essentially be referring to the same region. I just chose to put those equal signs in there so I could show you what this looks like if you use the bracket notation. And one more formal definition here. This one's pretty straightforward, and we've already talked about it. When a function f changes from increasing to decreasing at some point, CD, so this is a point, we say the function has a local maximum value of whatever d is. And that's what you get when you evaluate your function at c, so f at c, which equals d. And you have the same type of thing for a local minimum value. All right, just give that a quick read and make sure that that makes sense. Okay, let's move on and do our final part for this part of the lesson, which is, let's look at some examples. Okay, so here's a function. We're quickly going to talk about those properties for this function. And we'll start with the domain. Well, you know the domain for a parabola. This parabola continues to the right and to the left infinitely far, so the domain is all the real numbers for x. What about the range? Well, we have all the real numbers that are 4 or less. So there's our range. Y is an element of the real numbers such that y is less than or equal to 4. And where is this graph increasing? Now, don't let the downward pointing arrows here make you think that this graph never increases. Remember, we read from left to right to see where something's increasing or decreasing. And now as we come in from the left, we see that this function is actually increasing. So how do we say that? Well, where does it stop increasing? Right here. That's at an x value of -2. So as long as our x values are lower than -2, this graph is increasing. So we could write it like that. So from there to there, so like way back here at -infinity, all the way to -2, our graph is increasing. Now I will just tell you one more thing here about this notation. X is less than -2. That describes all the x values below -2. There are some other ways we could write that. So we have x is less than -2. You could say from -infinity, so way out far on the left side, up to -2. You could also use our bracket notation, say -infinity to -2. These are all the same thing. So just take a quick look at those and make sure that they make sense to you. Notice though that we never include -infinity. That's because it's not actually a number, right? You can't include it. You can never reach it. And because in this case we're talking about an interval of increase, we don't include the -2 either. Okay, so back to our graph here. What else do we have? Interval of decrease. Well, notice the graph is decreasing from -2 all the way off to infinity here. So we could say this graph is decreasing for x values greater than -2. We have an absolute maximum value right here. That's the highest the graph goes. So what is that value? It's 4, which is f at -2. We write that as just a courtesy to talk about where it's occurring. But this graph does not have an absolute minimum value because it continues downward infinitely far. So we have no absolute minimum. Do we have a local maximum? Well, we just need to look for that, that little bump, that little camel's hump in the graph. And we do right there have a local maximum. It's the same as the absolute maximum. But similar to our absolute minimum, we do not have one because this graph continues in the downward direction infinitely far. Okay, let's do another one here. We're going to be looking at these functions pretty soon. This is a different type of function known as a cubic function. We'll learn all about those in the near future. What is the domain for this graph? Well, it does continue to the right and to the left forever, so its domain is all the real numbers. Its range, well, this graph actually continues upward and downward forever, and it doesn't skip any values or anything. There's no breaks or gaps, so the range is also all of the real numbers for y. Where is it increasing? Well, we have an interval of increase from -infinity all the way to -2. So we could just say when the x values are less than -2, like over here and beyond, our graph is increasing. And when we have x values greater than 2, notice that from here as we move through these x values from left to right, greater than 2, that graph is also increasing. That just leaves us with our one interval of decrease, which is from -2 to 2. That graph is dropping down there. It's falling as we go from an x value of -2 to 2. So that's our interval of decrease. And if you want to use that new bracket notation, you can. Absolute maximum value? There is none. This graph continues upward forever, so we don't hit an absolute maximum. Absolute minimum? Same thing. Because it's continuing downward forever, there's no absolute minimum. We do have a local maximum value right here. In this region, this is a maximum. Its value is 4, also known as f at -2. Or in this case, it's g. The function is called g, so g at -2. And we have a local minimum value right here. It's that little valley. That local minimum value is -4, also known as g at 2. So there's a couple of examples describing some of those properties. Now let's try to draw a graph based on a description. Take a look at this description. So we're supposed to graph a function y equals f at x that has all of these properties. F at 1 is 2. Now this here just means f at 3 is the same as f at -1, which is 0. So f at 3 is 0 and f at -1 is 0. F at 0 is 4. So we have a bunch of points here, right? The point 1, 2 is on the graph, the point 3, 0 is on the graph, and the point -1, 0 is on the graph, and the point 0, 4 is on the graph. This can be a little bit confusing here. All this is saying is, well, let's read it first. F at x is greater than 0 for x less than -1. What does that mean? Well, f at x, that's the output value or the y value of our function. So it's saying your y values have to be bigger than 0 when your x values are -1. And we'll come back to this in a minute, but it's essentially saying whenever your x values are below -1, you should have positive y values. This is kind of the same idea. Whenever your x values are bigger than 3, you should have negative y values. Our domain is all the real numbers, and our range is all the real numbers from -4 through 4. So let's see if we can actually draw this. Okay, let's start with the points. That's probably the easiest part. F at 1 is 2, so an x value of 1 gives us a y value of 2. In other words, the point 1, 2 is on the graph. So we can just draw that right there. F at 3 is 0, so the point 3, 0 is on the graph. F at -1 is also 0. And f at 0 is 4. Now, the rest of this, we have to get perhaps a little bit creative. Let's think about the rest of the description for a minute here. When we're using x values that are less than -1, so that is like x values here and back, your y values should be positive. So we're going to need some graph up here, not down here. The y value is going to be positive. So just remember that for a minute. You need graph up here when your x values are less than -1. When your x values are bigger than 3, your y values should be negative. So as soon as we pass an x value of 3, your y values should be negative. So they should be down here. So you've got a graph where you have y values up here when you're in this region and y values down here. It doesn't tell you anything about what those y values are, but that's where they should be: positive on the left, negative on the right. You're required to use all real numbers for your domain. So this graph has to continue indefinitely to the right and to the left. But you got to watch your range. You're not allowed to go past -4, in the negative direction, or above 4 in the positive direction. Although you are required to cover all the numbers from -4 to 4. Wow, so how do we do that? Well, let me show you a possible graph. Now, this isn't the only one. There are many, many, many different possible answers for this that all meet these requirements up here. But in this case, I've passed through all the points. When my x values are less than -1, I do have y values greater than 0, so that requirement has been met. When my x values are greater than 3, I have negative y values. That's requirements met right there. My domain is indeed all of the real numbers. Notice these arrows, and I don't have any breaks or anything in my graph here. And for the range, I do get down to -4 right here. And I cover all the y values up to 4, which is required. But I don't go past 4 up above, and I don't go past -4 down below there. Instead, I chose to just kind of level my graph off around, looks like negative maybe 1.9 or something here, and around 2 going in the other direction. So that meets all the requirements. And like I said, that's just one possible graph. Let's do another similar example. This will be the final one for this part of the lesson. Take a look at this description here. So we're supposed to graph a function, calling it y equals f at x, that has all of the following properties. And let's just get started on this right away because we kind of know how to handle some of this already. F at -3 is 2. So when x is -3, y is 2. So the point -3, 2 is on the graph. So we can do that. F at 1 is -1. So 1, -1 is a point on the graph. Now, here's where it gets exciting. The function is increasing on the intervals -infinity to -3 and 1 to infinity. Now, -infinity to -3. So that's coming in from way far left, like, kind of forever, like as far as you can ever imagine beyond that from the left. That's -infinity. All the way to an x value of -3, the graph should be, increasing. So that means you're going to have to be coming up like this until you get to this point. That's from -infinity way back on the left up to that point at an x value of -3. It's also increasing from 1 to infinity for the x values. So here's 1, well, we have a point, so we have to go from there and we have to increase to the right, infinitely far, so like that. And we're decreasing from -3 to 1. Well, that kind of has to happen anyway, because from -3 to 1, we have to move from this point to this point. So we have to decrease there. Other than that, we have to cover all the real numbers for our domain and our range. So what could we do? Well, we can actually just use straight lines here. Here we are coming in from -infinity to an x value of -3, and we are increasing. We could then also do the same here, increase from an x value of 1 off to infinity for x, that graph is going up, and decrease from an x value of -3 all the way to an x value of 1. And because this graph goes to the right and to the left infinitely far, as well as up and down infinitely far, we are using all the real numbers for x and all the real numbers for y. So that's it. That will meet all these requirements. That's just one possible graph. Of course, you could have made it curvy if you want. There's different ways of building this, but you just have to meet all those requirements. So we're going to stop there right now. That's the first part of this lesson. There is a second part, so check that out, where we look at some other properties as well. But for now, let's leave it at that. There you go.